Hello. Oh, it's Advent of Code 2024! And we're looking at day 6 already. Look at that, we've already solved 10 challenges. Woo! And as always, I'm tackling these challenges in Funciton, an esoteric programming language that I invented, which consists of lines and boxes, Unicode box drawing characters, yada yada. You've seen my previous videos, you know what I'm talking about. Let's go straight into day 6. Day 6. Guard Gallivant. Okay, so apparently we have a map, that is the puzzle input, which looks something like this. And we're looking for a guard who is patrolling this map. And we have to work out where the guard will go ahead of time. Interesting. The map shows the current position of the guard with this caret to indicate the guard is currently facing up from the perspective of the map. Okay. Any obstructions are shown as hashes. Okay, those are obstructions. If there is something directly in front of you, turn right 90 degrees. Otherwise, take a step forward. Okay, so that's the movement rules for the guards. So this particular guard here will go forward up until here, because that's where they hit an obstacle. Then they turn right. They go up until here, turn right. Then they go here. Then they turn right. And then I assume they will go all the way up to here. And then here, and then here, and then here, and then here, and then here. And then here, and then here they will get stuck. Or rather, they will backtrack. Well, let's see. This process continues for a while, but the guard eventually leaves the mapped area. Okay, so when I said the guard stops here, they don't. By predicting the guard's route, you can determine which specific positions in the lab will be in the patrol path, including the guard's starting position. The positions visited by the guard before leaving the area are marked with an X. Okay. In this example, the guard will visit 41 distinct positions. Predict the path of the guard. How many distinct positions will the guard visit before leaving the mapped area? So once again, we're dealing with a two-dimensional grid, which we've done before on day 4, where we were doing something like a word search. So here is my implementation plan, or at least some kind of beta version, because I don't know if I'm going to modify it as I go along. The first thing I'm going to do is read in the input, obviously, but then I'm going to split it at the new line, so I'm going to have a list of lines of text. I can check the length of the first line to find the width of the grid, and I can count how many lines there are to get the height. And once I know the width of the grid, I can then represent any position in the grid by taking the y-coordinate. So for example, this would have the y-coordinate 2, because this is 0, this is 1, and then this is 2. Multiplied by the width and then add the x-coordinate, which in this case would be 5. That way every position on the map is numbered from 0 to the size of the grid minus 1. After reading in the input, I need to find out the position of the caret, which should be easy, and then I'll need to replace that caret with a dot. And then I need to do a kind of loop where I will just follow the path of the patrol. And in Funciton, we always do loops with, that's right, recursive functions. So I will have a function that I will give the grid and the position and the direction, and it will check what would happen if it advanced the position by 1. If we hit a dot, then we can just go there. If we hit a hash, then we have to rotate the position, I mean the direction. And if we go out of bounds, then we stop there. Now, meanwhile, I want to keep track of all the positions that we visited, but remember that we need to count the number of distinct positions. So we can't just make a list of them, because that list is going to have duplicates. So I'm going to keep track of the positions that were visited by having a single number starting out with 0, and I put a 1 bit in every position that corresponds to a grid position that we visited. And crucially, if I set one of the bits to 1 when it's already 1, then, it'll just stay 1. It won't be counted twice. So at the end, I can just count all the 1 bits, and it'll count only the distinct positions. So let's start again with a typical piece of code that will read standard input and split it at all the new lines, which is character number 10. Now remember, we want both the width and the height, so I'm going to take a copy of this, and I'm going to use the count function on one of them to get the height of the grid. And as for the other one, well, remember this is a lazy sequence of strings, and lazy sequences are lambda expressions, so we're just going to invoke that lambda expression to obtain the head and the tail, where the head is the first element, and then we need the string length of that to get the width of the grid. And let's label these. And now let's think about the recursive function that we want to write. What does that function need? Well, we definitely want to pass in the width of the grid because we need that in order to encode and decode grid positions into x and y coordinates. We also want the height of the grid because we need to know when we reach the edge of the grid. Then we also need the direction that the guard is currently walking in. And then we need that number with the 0s and 1 bits that I mentioned, where 1 bit is a visited square. So I'm going to call it visited. And on top of that, we also need the grid represented as a single string, which I almost forgot about. So let me quickly construct that by simply concatenating all of those lines from standard input with the empty string. Now, as I keep emphasizing in every one of these videos, the maximum number of things that we can pass into a function is 3. So we have to either pack multiple of these values into a tuple, or we can use the strategy that I used in the arrays video. Remember when I implemented binary search, I used a recursive lambda expression. I'm tempted to do that again because 3 of the things that we need, the width, the height, and the grid, are literally right here, and they will never change. So we can just capture them from the environment. Which means that our lambda expression needs 2 inputs, the direction and the visited, which we can do by simply stacking 2 lambda expressions inside of one another. So let's say that these are the inputs to our lambda expression. What does the lambda expression need to output? Well, at the very end, we really only need the final visited, because counting the bits in it, well, we're just gonna do that afterwards. Now, I think we don't actually need to pass visited in. Because think about this, the very first time we call the lambda expression, we're here, and then we're going to call the lambda expression recursively to process the next position, which then will process the next position, which means that the recursive call will essentially deal with the entire rest of the route. So the way we can think about this is that when the guard leaves the map, which they do by going down from this position here, then we return our first version of the visited thing, which will contain only that square. And then we return back to the previous recursive call, which would have been the position before that. And then that can add its bit. And then that can basically unwind backwards. So we don't need to pass in this visited, but I did realize as I explained this that we do need the position of the guard, not just the direction they're walking in. I completely forgot about that. Now I could use a nested lambda expression to pass 2 variables into it, but actually the direction is always going to be one of 4 different values and therefore always takes exactly 2 bits. So I think it will actually be more performant if I just put those 2 bits below the position. So I'm actually going to pass in only 1 value, and that value consists of the position, but shifted left by 2 bits, so we make room for 2 extra bits of information. And then we can use binary OR to put the direction in that extra slot. So that's going to be our only input. So we're going to implement a lambda expression, so we need a lambda expression box. Now this lambda expression is going to output only one thing, so for the second output, let's just always output 0. The input to the lambda expression, as we said, is going to be this. I'm going to call that the input, and the output that we need to pass into here needs to be the updated visited value. Now there are 2 cases to take care of. The first case is what if we run off the edge of the grid? In that case, we want to return a number that has a single 1 bit at the position that we're currently at. Now that looks like it's going to be a relatively simple formula, so I think I want to put that on the left so that the bigger rest of the program can be on top here. So I'm going to say not run off the edge, and then it'll be inverted. So this is now the not run off edge case, and this is the run off edge case. So we want a single 1 bit at the bit that corresponds to our current position. So we need to use the shift left function. Now we're gonna need to calculate the position from the input, which of course we can do by just shifting it right by 2 bits, just shift out the direction thing and that will reconstruct the position. But we're gonna need the position for the rest of the function as well, so I'm going to defer that until later. Let's now draw our attention to how to determine whether we're running off the edge. It turns out that we need to check 4 different conditions, one for every direction that we could be walking in, right? If we are walking outwards, then we would be running off the edge if our current y position is 0. If we're walking left, then it's the x position being 0. If we're walking right, then it's the x position being equal to width minus 1. And if we're moving down, then it's height minus 1. So we'll definitely need a question mark to distinguish those different cases. So what should the first condition on that question mark be? We need to check 4 different values for the direction, which we could do by just asking is the direction 0, is the direction 1, etc. But I think because the grid is going to be large, right? So we want to take care of performance a little bit. So I think an easier way to deal with this is to ask for each of the individual 2 bits that make up the direction. So I'm going to extract the bottom bit first, which we can do by doing a bitwise AND with 1. And then we need to ask for the second bit, which we can do by asking whether the direction AND 2 is equal to 0. So if direction AND 1 is true, then we'll be checking this, but if it is false, in other words 0, then we need to check that as well. And I just noticed I put this in the wrong place, so let me compactify this a little bit. I think it's easier to read without the spaces. Now I'm going to number the directions in clockwise order, going from 0 meaning up. So 1 will be right, and then 2 will be down, and 3 will be left. So let's see, if direction AND 1 is 0 or false, and direction AND 2 is also false, then we'll be going in direction 0, which is up. If direction AND 2 is true, then we'll be going in direction 2, which is down. If both of them are true, that'll be direction 3, which is right, and then the only one left is left. Now, what are the actual conditions we need to check for? If we're going up, then we need to check if y is equal to 0. And we can return that as a boolean. So the question mark that ultimately checks that condition, we can change that to an interrobang, which is the performance optimized version of the question mark for booleans. If we're going down, then we need to check if y is equal to width minus 1. But you know what? Y is never going to be any bigger than that. So we can actually optimize this by using greater or equal to here and less than or equal to here. Now similarly, if we're moving left, then we need to check if x is less than or equal to 0, and if we're moving right, then we need to check if x is greater or equal to width minus 1, and I got this wrong, this should of course be height minus 1. Congratulations if you paid attention and noticed that. Okay, let's pull this apart a little bit to make some space. And then let's implement those bitwise ANDs, which we do by using a bitwise NAND followed by a bitwise negation. Now, since we're looking at only the 2 bottom bits of the number, we don't actually need to extract the direction anymore, we can just use the input directly. So I'm just going to put input here. Now, to do the x greater or equal to width minus 1, we're going to need a greater or equal to, obviously. So let's place the y greater or equal to height minus 1. And the y less than or equal to 0. Now this place in the code is a little bit hairy. We have 2 things that are clashing with one another, but we can solve that easily because the direction AND 2 is the same value that we want down here. So I'm actually just going to take a copy of that and then pass that copy through a wire crossing function. Now as for the y less than or equal to 0, I think you'll agree with me that that is exactly the same as saying less than 1. So I'm actually going to use a y crossing function here so that I can reuse that 1 box at the bottom. Next, we see that we have a y here and here. Well, fortunately, we can just change the greater or equal to a less than or equal to swap the 2 operands. So this is now height minus 1, and this is now y, which means that we can now easily join them up. Now, this x here got moved, that was supposed to be here, and we're going to do something very similar here. So let's start by putting the less than or equal to here. And we're in the same situation as before, where it would be more convenient if that x were on the other side. So I'm going to change that greater or equal to a less than or equal to flip that around. And then we can join up the x's. Of course, we need to actually put a 0 box there, so let's make enough space for that. Now to get the h-1 and the w-1, we're gonna need to decrement the h and the w. So let's put in the calls to the decrement function right now. Now, I forgot something. Remember that when I wrote this here, I said I wanted the true case to be the case where we're not running off the edge of the grid. So that means that all of these conditions are basically the wrong way round. So I'm going to change this less than or equal to a greater than, this also to a greater than, this becomes a greater than, and this should be a greater or equal to. Okay, that is the entire condition on whether or not we're at the edge of the grid. Now, what if we're not at the edge of the grid? So now we need to look at the character that is right in front of us. So at this point, there are 2 things that can happen. Either that character is a hash, or it's a dot, and I'm just going to check for a hash and I'm going to treat every other character as a dot. Which incidentally will mean that we don't need to replace the caret that marks the starting position with a dot, because it's not a hash. So as long as it's not a hash, it can be any character. So let's put an interrobang here to separate those 2 cases. Now, in order to check if the character is a hash, I'm going to use the equals function, and the hash character happens to be Unicode value 35. So how do we obtain that character? Well, we need to index into that string, don't we? So let's use the substring function. The string that we're indexing into is the grid. The place in the grid that we want to look at, well, that is the position that we need to move to. So I'm going to call that npos because it's the new position after we've moved one step. And we want a single character, so the length of the string we want to extract is 1. Now, if we do in fact encounter a hash, then we need to turn 90 degrees to the right. And in all other cases, we need to advance one step forward. So at this point, I think I can compactify this bit. Now, both of these are going to be a recursive call to our lambda expression. So let's do the turn one first, and we're going to need a lambda invocation right here. We're going to be calling the same lambda expression that we're working on right now, so I'm just going to put that lambda there. The input, well, it's going to be this, but with the direction changed. Now, how does the direction change? Well, we always turn right 90 degrees. Now remember I said that up is 0 and right is 1 and down is 2 and left is 3. You can see that that is actually a clockwise order. So in order to turn right 90 degrees, all we need to do is add 1. But of course if we're moving left and the number is 3, we need to turn it back into a 0. So if the previous direction was 0, 1, 2 or 3, we want the new direction to be 1, 2, 3, and then in the case of 3, we want it to go back to 0. But what happens if we just add 1? Well, obviously we get a 4 here, but what is that in binary? Well, the direction is these numbers. So if we add 1, we get 0, 1 here, 1, 0 here, 1, 1 here. And then we get 1, 0, 0. But what we actually want is 0, 0. And all the other ones here give us what we want. So you can see that we only need to extract the bottom 2 bits. That's going to be much more performant than using the modulo function to do modulo 4. So let's erase this again. So what we want in here is the new direction, which I'm going to call ndir. And I'm going to write down what ndir is here. So it's the position shift left 2, or, well, it's the direction plus 1, which I can do using the increment function, bitwise ANDed with the bottom 2 bits, which is 3, because it's 1, 1 in binary. So let's scroll down a bit so we can still see the rest of the function. So on the top level, we need this to be a bitwise OR. So let's start by writing that. And now on the right-hand side of that, we have an AND, which we do by doing a bitwise NAND followed by a NOT, and that NOT will cancel out with the NOT that we already have. So we can just get rid of that and put a bitwise NAND with 3 right here. And what do we want to AND with 3? Well, it's an increment of something, so let's draw the increment function here. And the thing we want to increment is the direction. Now on the other side of the OR, we want to shift left something by 2, so let's put that right there. And with that, I think we've successfully calculated the new direction. But I think I got something wrong here, because what we want to pump into this question mark is of course the first output of the lambda expression, which means that this one here should be the second output. This one here is where we need to put the lambda in, and this is where we need to put the ndir, the new direction, in. Well, I could fix that by moving all of this over to the left and connecting this here, but this lambda needs to connect with this down here where the lambda actually comes out. So I think what I'm going to do instead is I'm going to rotate this 90 degrees clockwise, which means that this and this can stay in the same position, and we just need to have that one connect with the question mark. So let me start by connecting the lambda so that I know what the layout is going to look like. And now I can just move the invocation box a little bit to the right. But that leaves us with the second output of the lambda, which we want to ignore, so we need to put the flag construct there. Okay, so if I haven't made a mistake, then our lambda expression will go into here, and all we do is we just calculate a new input by just changing the direction to one that is 1 clockwise, and then the output of that is what we return. Now in the other case of that question mark, we still need to call the lambda expression, and this time we need to advance forward one step. So let's place a lambda invocation here. And this time let's make sure that I put the connectors correctly. So if this is the first output, then this is the second output, which we want to silence. So let's do that now. And then counterclockwise from that, we need to put the lambda expression in here. And then this down here needs to be our new input, which we calculate by advancing the position forward. Now let me scroll down a little bit, but there's obviously not enough space here to calculate that new input. So I think I'm going to do something very similar to here, and I'm going to rotate this 90 degrees clockwise. Let me quickly do that. So this time the lambda expression wants to go in here, and the new input can go right here. Now remember, we're already putting the lambda expression into this other box over here. So I think we can easily take a copy of that and then put it through another y-crossing function. And now you can see that I can actually put this a bit further up on this wire in order to make more space for the ni. And I can even save some space by having the flag point up instead of down. Okay, but now we eventually need to calculate the ni, so might as well do that now. Now, just like before, we do need to do the bitwise OR in order to put the direction back on. This time the direction doesn't change, but we still need to do the bitwise OR. So let's write that now. And since the direction is the one that doesn't change, I'm going to put that down here where there is no space, so that I can use all of the space up here to calculate the new position. But before we do that, before the bitwise OR, we need to shift that left by 2 bits in order to put in the direction. Now we don't need the new direction anymore, we've already calculated that. So in order to calculate npos, we need to either increment or decrement either x or y. And of course that depends on the direction, and we've already calculated something here on the basis of the direction. So we already have the bitwise ands that we need in order to determine what the direction is. So for the benefit of performance, I think I want to reuse them, but in terms of the geometry, this is not easy. But I will give it a go. Okay, so this is direction and 1. As for the other one, direction and 2, we're already splitting it into 2 copies here, and we're putting one of those copies here. But you know what? I don't actually know what the geometry is going to look like, so actually I'm going to defer that until later, and I'm just going to calculate npos first. So let's consider how we actually calculate the new position. Well, the new position is going to consist of a new x and y coordinate, right? So I'm going to call them new x and new y. And in order to calculate the coordinate, we're going to add them, but we need to multiply the new y coordinate with the width of the grid. So the whole thing is basically an addition, so let's put a call to the addition function here. And now before I box myself in, I'm going to move that 2 box down a bit, so that it's not in the way. Now on one side of that addition, we want the new x coordinate, and on the other one, we want a multiplication. So let's put a multiplication invocation right here. And we're multiplying the width times the new y. Now let me calculate the new x first, so that I get an idea of how big it is. So I'm not going to decide on where to put the w yet, so I'm just going to say that one of these needs to be w, the other one needs to be ny. Now, for the new x, there are 3 possibilities. Either we want to increment it or decrement it or leave it alone. If we're moving left, then we want to decrement it, and left is direction number 1, which is 0, 1 in binary. And if we're moving right, then we want to increment it, and right is direction 3. So that means that we need to modify it when the bottom bit is 1, which is the same as dir and 1, which we have down here. So I'm going to put a question mark to check for dir and 1 first. Now let's write a table of what we want happen. If the direction is equal to 0, which I'm going to write in binary, then the amount of change that we want to make to x, well, 0 is up, so that doesn't change at all, so that's a 0. Direction 1 is right, so we want to add +1 to x, and then for 1, 0, we want to keep it the same again, and then for 1, 1, which was left, we want to subtract 1. So if the bottom bit is 0, so if direction and 1 is 0, then we want to keep x unchanged. So I'm just going to put x in there. Otherwise, we need to look at the top bit, because if it's 1, we want to subtract, otherwise add. So we need another question mark. So if that is 1, then we need to decrement. And in all other cases, meaning it's 0, then we want to increment. Okay, in terms of its size, this looks pretty reasonable. In fact, I think I'm just going to put the exact same thing here to calculate the new y coordinate. But I do need to pull everything to the right a bit to make space for that. Okay, but this time, how do we want the y coordinate to change? Well, let's think about this. If 0, so 0 is direction up, so we want to decrement the y, and then if we're going left or right, we don't want any change at all. But if we're going down, which is direction 2, then we need +1. So once again, we want to check the bottom bit in order to see if we want to make a change. But this time, we make the change if that bit is equal to 0. So that means we need to flip the direction of this question mark. And, well, if you've followed my videos, you know that I have a function for this, which is basically this, which does the same thing as question mark, but with a true and false reversed. Now for the second condition, well, if this is 0, then we want to decrement it. So this time these functions are actually the other way around. This should be the decrement and this should be the increment. Which of course I could have done by flipping this one as well, but you know, it doesn't matter. Anyway, we want to put y in here. Okay, now the real big question is how do we route these d and 1 and d and 2 across the entire function in such a way that they can join up with this one here and this one. And I'm going to start with the d and 1. And I'm going to route it all the way down here and then over there and then join it up with that. But now we need a second copy of it here. So I'm going to scroll up a bit and then I'm going to use another wire crossing function to put a copy of it right there. Okay, so now if I haven't made a mistake, then d and 1 comes in here and it is split into 2 copies, one of which goes into this question mark and the other one goes into this question mark. So that should be fine. Now we need to deal with d and 2. And in order to deal with that, I'm going to put another round of wire crossing functions in the x portion of this code. Okay, now we need to connect that up with the code down here, which calculates d and 2. Now, this is one place where the d and 2 is used. So I'm going to use a wire crossing function here to liberate that, and then I can join them up. Okay, so much for that. Now let me zoom out a bit so we can see more of the function. And it has just occurred to me that I actually missed something, namely this npos over here. We need the same new position here that we're calculating here. So we're using the x and y coordinates here to calculate that position, but then we're shifting it left by 2. Before we do that, we want a copy of that. So I have to move everything up and take a copy of it, and then pipe that copy into that place where the substring function needs it. Now there are 2 places where we need x and y, the one up here and the one down here. So let's start by connecting up the x's. And then let's connect up the y's, which requires 2 wire crossing functions. Now, how do we actually calculate x and y? We have a position, which if you remember is calculated like this, like the original position is x plus w times y. So in order to retrieve the x and y from the position, we can do division and modulo by w. And the quotient will go in here, which takes me to the y. And then the other one, which is the modulo, I'm just going to connect that with this line, and that will pipe it into here where we need the x. Now, what are we dividing? Well, the position, of course, and we're dividing it by w. Okay, so now we have position here, and we have direction here and here. And we need to calculate these from the original input. Since the function is getting quite large again, I'm going to zoom out a little bit more again. So let me write that code over here. For the position, we need a shift left 2, so let me quickly write that. So this will calculate the position from the input. Well, except I got this wrong. We actually want shift right 2, but I'm going to express that as shift left negative 2 because shift left is more performant. Meanwhile, the direction is literally the bottom 2 bits, so that would be a bitwise AND with 3. And now that I can see the orientation, I think what I want to do is I want to put this code somewhere in here, but that means that I will need the pos to come out the left side and the dir to come out the right side. So I'm going to turn this upside down, and then I'm going to connect them up. And now I can paste that right into that empty space. Now I should have marked this with an arrow because pos comes out of here, but now that we're here, I can just connect that up with the two places that need the position. But joining up the directions is not going to be easy. Well, this is where the direction comes out. I'm going to actually mark that with an arrow now to unconfuse myself. And we need to pass it into here. Let's put a D there and into here. So in order to deal with this one at the bottom, I'm going to start by swapping this bitwise OR so that the dir is at the top. And now I can use a couple y-crossing function to bring that into the space where we need it. Okay, so we need this direction to go both into here and into here. So let's split it into two copies and get it over with. All right, so this humongous function that we have now, let's see, what else do we need to, oh yes, of course, input. Input needs to go in here and down here where we calculate the direction bits. So we need to use plenty of y-crossing functions, but nothing complicated. And what do you know, I actually forgot one occurrence of pos. So I'm quickly going to deal with that as well, which also requires a couple y-crossing functions. Now the only things that are left are w, the width, which also occurs down here, and down here, and of course h, the height. And the grid, let's not forget the grid. Since w, the width, occurs so many times, I'm gonna start with that. Now h occurs only once, so that's easy to join up. And then finally we have the grid down here. So we need to liberate that from its confined space. Now I could use some more wire-crossing functions here, but I think I'm actually just going to have it go all the way around the function. That's just funnier. Okay, so if I haven't made a mistake, then this is the lambda expression which calls itself recursively and which will return the visited bits. Remember that? But before we get to that, we first need to call it. What do we need to call it with? We need to call it with the starting position. So I actually forgot about that, and we should have done that before I connected up all the W's and H's, because I'm going to need the W in order to calculate this. But no matter, I think I'm actually going to turn that into a separate function, because I can. Alright, let me zoom in a bit so you can see what's going on. So this is where we process the standard input and we get a lazy sequence of strings. We're gonna need that, right? We need to look through that entire sequence to find the one string that contains the hat symbol. But then we also need to determine its index, so it actually makes sense to turn this into a function. So I want a function that will take that lazy sequence, as well as the width that we've already calculated, and it will find the index of which string contains the hat, that will be the y-coordinate, multiply that with the width, and then add the index of the hat within that string. That's the x-coordinate. So what it'll return is the starting position. Now I have way enough space there on the right, so I'm just going to move that wire crossing to the right and then take the copy of the width. And then I can also move this entire block a little bit to the right, so that I can then take a copy of this. So this will go into a function call that I'm going to put here. And since this is day 6 of Advent of Code, I'm going to use the 6 in a circle. And now we need to write that function. Now I've already thought about how I'm going to implement the function, and I've realized that I'm going to need a third parameter here, which is going to be 0. So I'm quickly going to put that in so that I don't have to come back to here later. Okay, so the order in which we're passing the arguments is the sequence, the 0, which I'll explain in a second, and the width of the grid. So let's start by writing a declaration node for that function. And now let's think about what this function needs to do. Well, first of all, I'm going to assume that there is going to be a caret in the input. If there isn't, I don't mind the program crashing. So I'm not even going to check if lines is empty. I'm just going to assume that there is a line yet to be processed. So I'm going to call the lines sequence in order to obtain its head and tail. Now the behavior of this function that we're writing hinges on whether or not that head contains the caret character. So we need to check for that. So let's put a question mark for that. Now if it doesn't contain the hat, then we need to do a recursive call on the tail. Right, but if we do that, we need to keep track of how many heads we've already removed in order to know what the y-coordinate is, right? We need to know where in the sequence we are. And now you know what that n is. That's actually the y-coordinate that we're currently looking at. So I want to do a recursive call in which I increment that y-coordinate and then pass in the tail. Now, how do we actually check if the head contains that caret? Well, we have a function that finds us the index of a first occurrence of a substring, and the hat would be the substring that we're looking for, and it'll return -1 if that is not found. Also take note that we pass in the haystack, that's the string we're looking through, first, and then the string that we're looking for. So what we actually want to check for here is whether the index of function that I just talked about, when given the head and the string with the hat, returns -1. Or rather, doesn't return -1. In other words, it needs to be greater or equal to 0 in order for the true case to be the one where we find it. So what do we want to have happen here? Well, not only do we now know that it does contain that, we also know where, because that function actually tells us the index. So that will be our x-coordinate. So we need to add that onto width times the y-coordinate. So let's put the addition box here. And since this is the x-coordinate, wait, I forgot to do the comparison. Let's quickly put the greater or equal to 0 here. And we end up with the arguments the wrong way around, so I'm going to change that to a less than or equal to, so that instead of index greater or equal to 0, it'll say 0 less than or equal to index, which is the same thing. Okay, so this is where we put that index in here, and then we can also put it here. Okay, we've actually taken care of this comparison, so why don't we write the index of invocation next? Now the caret is actually Unicode character 94, and that needs to go on the top. Alright, now let's continue with this calculation of the coordinate. We need to multiply y and width, so let's put a multiplication box here. Now this is going to be the only place where we need the tail. So let me join that up with where it comes out of that lambda invocation. And then we have a y here, and we have the multiplication which needs a y on one of its sides. So I'm just going to put the y on the left side here. Now we need the other side of the multiplication to be the width, and of course we also need it down here in the recursive call. So let's join these up, and then we need just one more y-crossing function to join up the head as well. Okay, with that function under our belt, let's go back to the main function where we are calling it, and that is here. So this will be the starting position, and we need to pass that starting position into the lambda expression, which comes out of here. So let's start by routing that lambda expression all the way up to the top. Okay, so we have the starting position come out of here, and we have the lambda come out of here. So if I haven't made a mistake, all we need to do now is call the lambda with the starting position. Okay, so we have lambda and input, and then this is where the actual output comes out. And this is the second output that we don't care about, so I'm quickly going to silence that. And remember, the output of our lambda expression is actually this number with lots and lots of 1 bits for all of the visited positions. So we still need to count the number of 1 bits in that number. So I'm going to write a function for that too, so let me quickly invoke that function right here. And then whatever comes out of here is going to be a number, so I want to turn that number into a string for output. And then that should be the final output of our program. So all that's left to do now is to write this function. So let's start by writing the declaration box. And like all good recursive functions, we need to start with a terminating condition. So let's check if our input is already 0. Well, if the input is 0, then the answer is 0 because there aren't any 1 bits in it. Otherwise, we need to check the lowest bit of input. If that is 1, then we want to increment, and if it's 0, then we don't, which is actually the same as just adding that bit, right? So I'm just going to use a bitwise AND to obtain that bit and literally just add it onto the recursive call. Now I could put the recursive call on either side, but because the bitwise AND with 1 is going to reuse the input, I'm going to put that on the right. And then on the other side, we just put the recursive call. And the thing that we put into that recursive call is the same input, so we just join that all up. Now let's just take another quick look at the humongous main program. And I've decided to put the 2 functions that we wrote on the side. Okay. So, if I haven't made a mistake, then that should be it. So now it comes time to actually run this. Alright, I'm quite nervous because we haven't tested any of the intermediate functions or parts, but let's just run this on the example input and see what happens, turns out we get an error message. Incorrect number of connectors to call to function substring. Not substring, index of. Well, the function I wanted to call is this one here, which looks like a dot in a circle, but I know that this is actually a symbol from the International Phonetic Alphabet, whereas the function name that I actually typed is this one here. It's one of the regular expression functions that I wrote off camera, which also looks like a dot in a circle, but this one is like a circle multiplication operator. So let's quickly change that. I know that this is hard to read at this font size, but you just gotta trust me here. And then we just run the same thing again. And this time, okay, we're not getting an error message yet. And it seems to be taking quite a while, despite all of my efforts to optimize the performance here. But it's always possible that I made a mistake and it's actually stuck in an infinite loop. So I'm going to let it run for a while, and then I'm gonna come back when it's finished, or maybe after an hour or so I'll cancel it and then I'll check for bugs. Well, that program ran forever, so I cancelled it. It looks like there is an infinite loop in it, and in fact, I think it's in this function. Did you spot my mistake? Do you want to pause the video here to see if you can fix the function? Are you back? Alright, let's get into it. So, what are we doing here? We're checking if the number is 0, and then the answer is 0, and then we want to add, well, we want to add the last bit to... That's right, we want to add it to the result of the rest of the number. But I'm just calling the function recursively with the exact same input, so of course this is an infinite loop. What I actually want to feed into the recursive call is the number shift right 1, right? We want to move on to the next bit. And as usual, I'm going to express that as shift left -1. Now, I believe that there was one other mistake that I made in the big and complex function. If my theory is correct, then this program should run and it should return the number 1 instead of the correct answer. So let's see if I'm correct about that. Let's run this with the example input, and I claim, there we go, it gives us a 1, like I thought. But it's actually supposed to give us 41, right? So obviously 1 is not the right answer. Now, to find out what is wrong, let's take another look at that lambda expression that we wrote. So the first thing the lambda expression does is it checks a condition, and that condition is whether we are at the edge of the grid and we are about to run off the end of the grid. And if that is the case, well, then we take the current position in the grid and shift it left by 1 in order to get that 1 bit in the position that we are. Now, in all other cases, we want to either move forward or turn 90 degrees, but we also want to count the position that we're on. We need to mark it as visited, and that's the part that I forgot. So what we end up doing is we end up using that 1 bit only at the very end when we run off the grid, and that is why the answer was 1, because that's the only bit that ends up being set. So in order to fix this, I want to return 0 from this else case, and then whatever comes out of here, which is the result for this particular position and everything that comes after it, we want to bitwise OR that with this, in all cases, not just the false case for this question mark. So let's start by applying a bitwise OR to the result of that question mark. Now I want one side of that OR to be the result of the question mark, but the other one needs to be the result of this shift right. So let's move that around so that the result of that goes in there. Okay, let me quickly recap just to convince myself that this is now correct. We have our lambda expression and its result is a binary OR, a bitwise OR. Ooh, I wrote this wrong. Good thing I did the recap, otherwise I might not have noticed that. Okay, so we want to bitwise OR the result of this, which is 0 if we run off the edge of the grid. Otherwise, it's the result of a recursive call, which is either this one or this one. We didn't change that, so I'm going to assume that's still correct. And we want to bitwise OR the result of that with a single bit, which is 1 shift left, the current position. So let's give that another go and hope for the 40... Woo! Cannot have more than one program output. Okay, that must mean that I didn't join up some line. Let's see, line 70, character 69. Indeed, we have an extra line here, and now I've forgotten what that was. I remember. Okay, so this is where we pass the lambda into the main call for the function, but we also need to pass it in here in order to call in order to perform the recursive call. Okay, let's see if I can connect that up. But I'm willing to bet that this is going to give us an error message similar to something we had in another video. But let me first check if that is actually the case. So I claim, yeah, okay, so this error message is not actually, it's not factually true. The main program doesn't have a cycle in it. But the part of the interpreter that tries to detect such a cycle has difficulty noticing that these calls to the lambda expression are inside the lambda expression, because we have a y-crossing function outside of the lambda expression, and the y-crossing function doesn't get optimized away until later, until after the cycle detection. So I have to pass that through here before I split it off into the part that is not inside the lambda expression. Hopefully that will have taken care of that. So let's run this one more time, and this time we get the number 2. I expected a 41. So, that is not quite working yet. Well, on closer inspection, I found another problem. I'm not entirely sure if this one explains why we're getting a 2, but let's fix it regardless because it is a bug. And that bug is somewhere in this code, which, if you remember, determines whether we're about to run off the edge of the grid. So down here, we are getting the input from the lambda expression. So we're passing that into here. So then we check here the second bit. Now if the second bit is true, then the number is 1, 1, which is 3, which is left. Well, it turns out that we're checking if x is less than width minus 1, and the less than 0 is over here. So those two are actually swapped. Now, fortunately, I can swap them easily by just changing this to the inverted question mark. So let us just try that. Now, I have no confidence that this is going to be any better. Ah, indeed, it gives you a 2. So, back to the drawing board with even more debugging. Okay, now I think I have actually found the main bug. If we look at this piece of code, you remember we wrote this function whose only purpose it is to determine the starting position, to find out where the up pointing hat, the caret, is. And we pass that directly into the lambda expression. But that's not the input that the lambda expression expects. It expects the position shifted left by 2 and then with the direction added in the lowest bits. Well, the starting direction is always up, which is always 0, so we don't need to worry about that, but we do need to do the shift left too. So let's quickly add that shift left operation before we pass the value into that lambda expression. Now this time I'm actually confident that that is the kind of problem that would cause the wildly wrong output that we've been seeing. So let's give that another go and hope that this time we are going to see a 41! Hallelujah! Okay. So just to remind ourselves, 41 is indeed the correct answer according to the puzzle page. So now all that remains is to run it on the full input, which is quite extensive, and I'm going to use the -m option to get some measurement on how long it took and how much RAM it used. And there we go, it didn't even take that long, it only took 27 seconds. That's quite encouraging. We only needed 131 lambdas. Remember that every element in a lazy sequence is a lambda, so that makes sense. I'm a bit surprised by the use of 100 megabytes of memory, but since I didn't have that -m option in all of the previous challenges, except for the one that took like 30 gigabytes, I don't really have a point of comparison. So I guess we'll see if 100 megabytes is a lot or not going forward. Anyway, long story short, I'm going to take the answer, and then I'm going to paste it right here at the bottom of the page. And it turns out that's the right answer! You are 1 gold star closer to finding the chief historian. Now that was definitely quite an adventure, especially with those 3 or 4 rather significant mistakes that I made, which required quite some extensive debugging to figure out what was going wrong. But anyway, we solved it. Now while the program was running, for 27 seconds, I thought a bit about what the sequel challenge might be, and I'll be honest, I have no idea. I'm not even going to hazard a guess. I'm just not as creative as the creator of these challenges, apparently. So, I'm gonna let it surprise me, and I'll see you in the next video where we'll unveil the mystery.